If we combine the properties of acid-base reactions with the idea of molarity and combine that with the ideas from stoichiometry, we can arrive at something called a titration. Titrations are a standard way of measuring the concentration of an unknown acid or base solution by measuring how much of the other substance you need to exactly react with it. And this is the subject of section 6 in chapter 4, the last section in this chapter. So let's look at these ideas. We're really using previous ideas, stoichiometry. We know balanced chemical equations give molar ratios, and we can get to molar ratios from molarity, concentrations. And we know properties about acid-base reactions. We know that if they involve a strong reagent, they are rapid and complete so that we can assume that when we mix things, they react. So let's just look at some examples of some stoichiometry type calculations involving concentrations. We have 25 milliliters of 10th molar hydrochloric acid, and we react with just enough 0.05 molar calcium hydroxide to react. How many millimoles of calcium hydroxide are consumed? From the wording of the problem, we see that this problem is asking about amounts of material related to each other by a balanced chemical equation. So the first step in any stoichiometry problem is write down the balanced chemical equation. So here we have a reaction between HCl, I'm just going to write it above here, plus calcium hydroxide. And we know an acid and a base react to form a salt, in this case, calcium chloride, and water. Acid plus base reacts to form salt and water. And now we have to balance it. So we look at, for example, the chlorides. I have 2 chlorines on the right. I need 2 on the left. That gives me 2 hydrogens that can react with the 2 hydroxides to form 2 waters. And now I have a balanced chemical equation. So if I want to find the number of millimoles of calcium hydroxide consumed, I can set that up from the information in the problem. I start with 25 milliliters of the 10th molar hydrochloric acid. I multiply it by the concentration of the acid, 10th molar, and I'm just going to rewrite that. Remember, we saw in molarity, I could think of that as millimoles of HCl divided by milliliters. That's the same thing as moles over liters. The millis cancel out. That will give me millimoles of HCl. And then I do a conversion using this stoichiometric ratio. So I want to cancel out millimoles of HCl and replace it with millimoles of calcium hydroxide. Hopefully that's not too small to read. Sorry, a little bunched up. And I get those numbers from my balanced chemical equation. Right, the 2 goes with the HCl, and a 1 goes with the calcium hydroxide. So I take 25, I multiply by 0.1, I divide by 2, and I get the answer, 1.25 millimoles of calcium hydroxide. Three significant figures. Now, if I want to know what volume of calcium hydroxide solution is needed in order to provide me with 1.25 millimoles, I just go back to my definition of molarity. It's moles divided by volume. Here, excuse me, what we want to calculate is the volume, so I rearrange my equation for volume. And then I plug in my values. N, here, I'm going to do it in millimoles. There's no point in converting back to moles. You can do it if you really want to, but it's a waste of time. 1.25 millimoles divided by the concentration of the calcium hydroxide. Make sure you get the right concentration. So that's 0.0500 molar. And here I'm using again the idea that molar is the same thing as millimoles per milliliter. So the millimoles will cancel out, and I'll get my volume in milliliters. And to 3 significant figures, it works out to be 25.0 milliliters. All right, So if we look at titrations, the idea is how can we use this to determine the concentration of a base solution? If we know an acid solution, know the concentration of an acid solution, how can we use that to find the concentration of a base solution? Well, what we do is we set up a burette stand with a burette so that we can drip a standard solution from the burette into an unknown solution. So typically we'll have the acid here. The standard solution is a solution of known concentration. It's used as a titrant. When we say the word titrant, what we mean is the stuff that goes in the burette. That's the titrant. It's what's being titrated into the flask. And then we titrate it to the equivalence point, and an equivalence point is when we've added just exactly enough of the acid to react with the base that's present in the container. This is known as the analyte. The stuff that we're measuring is what's in the container. And when we just add enough, that's the endpoint, and we can use that to calculate how many moles of base were present in the analyte. Now, how do you know when enough titrant is added? Well, the key to this in doing a titration is that we use an indicator. An indicator is an organic chemical that changes color when the acidity reaches a certain level, just like these words did. Now, as kind of an aside, these are not the most important points, but technically, the indicator changes the color at an acidity level that is characteristic for that particular molecular indicator. And what we really need to do is choose a proper indicator that will change color close to the equivalent point. Technically, where the color changes is referred to as the endpoint, which is slightly different than the equivalence point. The equivalence point is when we've actually added the equivalent number of moles. And we use titration error to indicate the difference between the equivalence point and the endpoint. Most of these are technicalities for the titrations we'll be doing in general chemistry, because we'll be doing strong acids with strong base, and all of the indicators that we use for that. We always use phenolphthalein, which is a great indicator for strong acid and base. It leads to very little titration error. And phenolphthalein is clear and colorless in an acidic solution. And when the solution just turns basic, the solution turns magenta. And that's how you tell when you've added enough base to the solution. Now, let's do a quick calculation example of a titration. Suppose we have a standard solution of 0.1440 molar sulfuric acid, and we use that to titrate 50 milliliters of a sodium hydroxide solution. So the sodium hydroxide is in the beaker. We're dripping sulfuric acid into it. We start with 50 milliliters of the base. It's important to keep track of which volume goes with which substance. The volume at the equivalence point is 35.43 milliliters. That means this much of the acid has been added. Okay, so let's find the concentration of the sodium hydroxide solution. The first step, as always, for any titration, any stoichiometry problem in general, is to write a balanced chemical equation. Now, this is not a balanced chemical equation. It is showing an acid plus a base goes to a salt and water, but we still have to balance it. So if we have 2 sodiums on the right, we need 2 sodiums on the left. That gives us 2 hydroxides, which will react with the 2 hydrogen ions from the sulfuric acid to give us 2 waters, and now it's a balanced equation. Make sure your equation is balanced. Then we can calculate the number of moles of sodium hydroxide at the equivalence point. We start with the volume of acid added, multiply it by the concentration of the acid. Again, that's from the problem. That will give us the number of millimoles of H2SO4. We then use the stoichiometric ratio, and again, the stoichiometric ratio is from the balanced chemical equation. That's where I get that 2 from the balanced equation. That converts from millimoles of sulfuric acid to millimoles of sodium hydroxide. So we get the answer, 10.20 millimoles of sodium hydroxide. And then we can find the concentration by dividing our millimoles by the volume of the original solution. Again, that's coming from the problem. That's the volume of the original solution. That's the solution we're interested in. And we get the answer 0.2041 molar sodium hydroxide.